In this video, we're going to take a look at the examples for AP Physics 1, Unit 5 notes on momentum. Remember to pause or rewind the video as you need to. Let's begin. We're on page 2 of the notes, and go ahead and scroll until you see the example on the screen here that says car crash example. Read along with me, please. A toy car of mass 2 kilograms and a toy truck of mass 4 kilograms travel in opposite directions with speeds of 6 meters per second. The car moves to the right and the truck moves to the left. If the two toys collide and lock together, in which direction will they be traveling? Diagram the situation and use your diagram to answer the questions. Okay, so let's figure this out. The car moves right and the truck moves left. Car, positive momentum, truck, negative momentum. So car, momentum of the car, which I'm going to call P1 initial. It's momentum of object 1 before the collision, is mass times velocity. So we're going to go uh, 2 kilograms times 6 meters per second, and we get 12 kilograms meters per second. And I'm going to color code this in terms of, I'm going to do yellow, blue, and then the final momentum is black. I'll do that. So the initial momentum of the car, initial mass, 2 kilograms. So each unit's going to be 1, and then 6 meters per second. So I'm going to shade in 12 of these boxes, just like this. All right, let's take a look at how the bar graph makes sense to us. We have 2 boxes shaded. There's our 2 kilograms right there, mass 2 kilograms. We have 6 boxes shaded here. There's our 6 meters per second right there. Now the truck, let's calculate the momentum of it. Would be the momentum of the truck would be P2 initial. Momentum of object 2, initial means before collision. And again, it's also MV, but that one's going to be 4 kilograms and moving negative 6 meters per second. It's moving to the left in the negative direction. That would be negative 24 kilograms meters per second. Well, keep in mind, it has a mass of 4 kilograms. So I'm going to be going over 4 and down 6 in terms of how I shade it. I'm going to use blue to shade the truck. So I'm going to go over 4 and down 6. Now, if you look at this, what do we have? Well, we have 4 kilograms of mass and negative 6 meters per second. Now, there's clearly more momentum going on with the truck than the car. I mean, 24 is larger than 12. So the overall, let's figure this out. What is the total momentum before collision? Well, the total momentum would be 12 plus negative 24. The initial momentum is equal to negative 12. Now, kilograms meters per second. Now, since the final momentum is supposed to be the same as the initial momentum, because momentum initial equals momentum final, that is conservation momentum now, the final momentum needs to also be negative 12. I'll shade this one in black. Keeping in mind, of course, that the total mass has come together in terms of 2 plus 4, which would equal 6. So the total mass would be 6, and then it's going to slow down because it's a larger mass, right? But it's going to have a total momentum of negative 12. So the system will be moving in the negative direction at the final velocity would be 2 meters per second to the left. And I think that's all they were asking. Which direction will they be traveling? To the left, and 2 meters per second will be the speed of that. Exploding sports car example. Well, we got the same cars. This time it's a 2 kilogram car and a 6 kilogram truck. They're initially locked together. They explode apart in different directions. Diagram the situation. Then answer, what is the ratio of the car's final speed to the truck's final speed? Okay, so their initial momentum has to be 0 because they're locked together. They're not moving. So and P1 initial is 0. P2 initial, 0. 0 momentum beforehand, so there's nothing, okay? But now, the car's final momentum, well, here's how we can kind of figure this out. The momenta of the car and truck are equal and opposite. Okay. Now, it doesn't say which direction, which one is which, so I'm just going to put the car on the left side and the truck on the right side. It means when they explode, the car is going to explode to the left in the negative direction, the truck's going to explode to the right in the positive direction. So let's try this. We're going to let M1 be the car, M2 be the truck, which is 3 times M1. 6 kilograms versus 2 kilograms. Okay, we know that if our conservation momentum equation, M1V1 initial plus M2V2 initial, that's M1V1 plus M2V2 equals M1V1 prime, that's final velocity, M2V2 prime. That's 0 and that's 0 because there's no momentum before collision. Therefore, if you take one of these and subtract it to the other side, you'll get that M1V1 prime is equal to a negative M2V2 prime. If I rewrite this, M1V1 prime is equal to negative 3 M1V2 prime. Okay, well, the M1s will cancel. And what that tells us is that V1 prime is going to be negative 3 times that of V2. So there's our ratio right there. If I divide by V2, the ratio of V1 prime to V2 prime is equal to negative 3. Okay, and so what that means, the car's final velocity will be 3 times the truck's final velocity, right? And this is because the car has 1/3 the mass of the truck. So how could we represent that in a picture? Well, how do you make the truck 3 times massive and 3 times slower? Well, here's how you could do it. You could make the truck with 6 mass units here going 2 meters per second forward. And when they explode, the car would be, which is 1/3 of that, 2 mass units is going to go 3 times faster, or 6 meters per second, but in the negative direction. In this next example, we're going to look at 4 cases in which a bullet can be shot into a block and either pass through the block or become embedded in the block, or rebound off the block, I guess we could say. But we have 4 different cases and 4 different situations we're going to look at. Let's read the question together. Consider a 2-kilogram bullet shot with an initial speed of 6 meters per second at a 4-kilogram block. The block is on frictionless rollers. The bullet collides with the block in a different way in each of the following cases. Case 1. The bullet goes through the block so that the bullet has a final speed of 4 meters per second after it emerges from the block. Case 2. The bullet embeds itself in the block so that the bullet and block become a single object. Case 3. The bullet strikes the block and drops to the floor. That means it hits and rebounds backwards afterwards. Case 4, the bullet bounces off the block so that the bullet's final speed... Case 4 is the case where we rebound backwards. Case 3, it hits it and just simply falls and drops with no momentum at all. First, take a moment to rank these from rank them in terms of the block moving forward fastest to the block moving forward slowest. Go ahead and pause the video. Make your ranking right here. Okay, now what we're going to do is we're going to complete the diagrams on the following 2 pages for case 1, 2, 3, and 4. Then we're going to come back and we're going to put the correct ranking here, and we're going to see how close you were with your prediction. Okay, then it will give a paragraph length response that explains our cases. Now, case 1. The bullet goes through the block so that the bullet has a final speed of 4 meters per second as it emerges from the block. Okay, so I'm going to call M1 the bullet and M2 the block. Actually, I don't have to call it that way. They're calling it that way. So this is M1 bullet, M2 block. All right, so the bullet itself has 2 kilograms and is going, and I'm going to color code this with black bullet and blue block. So we're going to be going 2 kilograms at 6 meters per second. There's our initial momentum here. And we'll go ahead and calculate things along the way too. P1 initial would be 2 kilograms times 6 meters per second, or 12 kilograms meters per second. The block's initial momentum, well, it's at rest, so there should be nothing. So the initial momentum, P initial, is 12. Keep that number in mind. Total initial momentum, total momentum between objects 1 and 2, it's due to that. Now afterwards, both objects are moving. let's start with the block. The block has 2 kilograms of mass, or excuse me, 4 kilograms of mass, and let's see how fast it would be going. Oh, I'm sorry. The best thing to do is start with the bullet because we know the full information with the bullet. The bullet is 2 kilograms, and it's going at 4 meters per second. So the bar graph for the bullet would look something like this. There we go. Okay, now the block's final momentum, see, if you think about it, you're supposed to have 12 before, which means the final momentum, P final, also has to be 12. Well, you already have 8. So now what we need 4 more. Well, if the mass is 4 itself, that means that it's going to have to be 4 kilograms and 1 meter per second. So that means the final velocity, which I guess we would call this V2 prime, would be 1 meter per second going forward. Okay, now what type of collision is this? Well, what you do to find out if it's an elastic or an inelastic collision is you find kinetic energy before and after the collision. So let's do that. Kinetic energy before the collision, 1/2 mv squared. The only thing moving before collision is the bullet. So 1/2 times 2 times its speed squared. That's going to cancel, leaving you with 36 joules. So the total initial kinetic energy, which is only due to the bullet, is 36 joules. The final kinetic energy has to be the sum of the bullet and block, because afterwards they're both moving. So it's 1/2 times the bullet's mass times 4 meters per second squared, plus 1/2 times the block's mass times 1 meter per second squared. So that was going to be 16 plus 2, or 18 joules. Okay, basically, we lost half of the kinetic energy. So since kinetic energy is not conserved, this is what is called an inelastic collision. Again, your evidence, ladies and gentlemen, is right here. An elastic collision is one in which the kinetic energy is conserved along with the momentum. Momentum is always conserved, right? But when kinetic energy is also conserved, it's an elastic collision. When kinetic energy is lost and obviously not conserved, then it's an inelastic collision. Case 2. So we've got the same combination, same bullet, same mass, same speed. So I'm going to start with the same amount. There. And I'm starting with the same information. P1 initial, that's the bullet. It's 2 kilograms times 6 meters per second, or 12 kilogram meter per second. Now in case 2, the block is also at rest. So P2 initial is still 0. So P initial is still the 12. The final needs to be the 12 as well. But the mass is now added up to 6. Well, 6 times what? 6 times what equals 12? Well, it has to be 2, of course. So we're going to go and we're going to make a bar chart that would look like this, showing you the combined 6 kilograms of mass and their coupled speed of 2 meters per second. What type of collision is this? Well, again, let's find the kinetic energy before and after, and we'll determine. The kinetic energy before is still 36 joules. That didn't change because the information is the same. The final kinetic energy, however, 1/2 The mass is now 6 combined kilograms times 2 meters per second squared. So half of 6 is 3, times 4 would be 12. So it's actually gone down by sticking together. It's actually gone down compared to when it passed through. Right, the kinetic energy is reduced by a third. So kinetic energy not conserved. This again, of course, means this is an inelastic collision. Case 3, we start with the same initial conditions, which are P1 initial is 2 kilograms times 6, or 12 kilogram meters per second, and the block is still without momentum. So the total initial momentum is still 12 meters, or kilograms meters per second. Now, the bullet comes to rest, so the bullet has no momentum. What that means is the block needs to carry over the 12 kilogram meters per second. But if you think about it, it's the bullet and block have become embedded. The bullet, it's not embedded. So the final momentum is 12. The final speed is going to be the momentum divided by the mass. So the momentum has to be 12. The mass is 4 kilograms. That's going to give you 3 meters per second. Okay, so 3 meters per second times 4 kilograms gives you 12. And you can see there's your 12, there's your 12. Momentum is conserved. Let's see what type of collision this is. Well, initial kinetic energy is 36 joules. That didn't change. The final kinetic energy is going to be 1/2 times 4 times 3 squared, which is 2 times 9, or like in case 1, 18 joules. Kinetic energy is not conserved. That means this is an inelastic collision. Case 4, again, we start with the same initial conditions. P1 initial is 12 kilograms meters per second. P2 initial is 0. This time you have a bullet bouncing backwards. So the total momentum, so the backwards, let's do that one first. The backwards part would be 2 kilograms and 2 meters per second. So it's going to be 2 by 2 in the negative direction because it's going left. There's your 2. There's your 2 kilograms. Okay, but it's negative. So what do we have to be doing? You have to have an initial momentum of 12. And since momentum is conserved, your final momentum has to be 12. Well, if this is -4, what we're saying is -4 plus what equals 12? Well, how about this? P final equals P2 final, P1 final minus P2 final. Plus P1 final plus P2 final. And let's just solve it for P2 final. So P final minus P1 final equals P2 final. So P final is supposed to be 12 kilograms meters per second minus the negative 4, which should be 16. That's what we have left over here. Okay. Kinetic energy, 36 joules. Final kinetic energy is going to be 1/2 times 2 times 2 squared. Doesn't matter that it's in the negative direction. Be 4 joules. I should say we got to add this, so it's not going to be just 4 joules. It's going to be 4 joules plus 1/2 times 4 times 4 squared. So that's going to be 2 times 6. So we have 16 times 2 is 30. Not 36. 16 times 2. 16 times 2 would be 32 joules. There we go. So we got 32 plus the 4 equals 36. Kinetic energy is conserved. That makes this an elastic collision. Okay, so if we move back to page 3, complete the diagram on the following 2 pages. Well, we did that. Now we're going to come back and we got to put the correct ranking of the block's final speed after collision. Well, let me just kind of summarize what we just did. We found that in case 4, the block was moving at 4 meters per second. In case 3, 3 meters per second. You can see by the height of the chart over here. Case 2, 2 meters per second. And then case 1 meters per second. So literally it's 4, then 3, then 2, then 1, in that order. So our paragraph length response really just kind of summarizes all this. In each case, the momentum was found for each object before and after the collision. Since momentum is conserved, the momentum before the collision was equal to the momentum after collision. Since P equals mv, we solve for velocity in order to rank the final speed of the block after collision. The block with the greatest speed is case 4 because it has the greatest final momentum after collision. This is because block 1 rebounds and has negative momentum. The block that has the next greatest speed is case 3 because it has the next greatest momentum after collision. This is because the bullet stops and has no momentum afterwards. The block with the next greatest speed is case 2. This is because the bullet passes through the block and only transfers some of its momentum to the block, and therefore the block moves more slowly afterward. If we find this section, 5.4, the generalized impulse momentum principle, let's take a look at the following set of examples. In this example, we have cart 1 rolling without friction toward cart 2 on a horizontal track. The 2 carts collide and separate. The positions of the carts 1 and 2 are shown as a function of time in the graphs to the right. We are also told that cart 1 has a mass of 0.3 kilograms and cart 2 has a mass of 0.5 kilograms. First question would be, during what 2 times does the collision take place? Well, take a look carefully at what's going on the graph. Remember, this is a position versus time graph. A straight line, this is great review for kinematics graphs here. A straight line was showing you constant velocity, this straight line is showing, again, constant velocity, which means this curve right here, that's where the acceleration takes place. That's the collision. The collision takes place when the momentum changes. Again, we can see it over here. Position of cart 2, constant velocity of 0. This part right here, constant velocity. And this part right here is showing you the exact same time interval. So it takes place from 2 seconds to 3 seconds. The collision takes place when the velocity changes. The slopes on the position time graph change between 2 and 3 seconds. Therefore, the collision takes place between 2 and 3 seconds. Find the initial and final speeds of cart 1 and 2. Okay, well, basically we're going to find the slopes. That's how we're going to figure out the speeds. So initial speed of cart 1 would be this part right here. And you can see you're going up 0.4 in over 1 second. So 0.4 meters per second before it collides. The final speed of cart 1 is the downward slope. So you're going down 1, 2 over, so you're going down 0.1 over 1 second. I think I'm seeing that right. Yeah, down 0.1 over 1. So negative 0.1 meter per second. The initial speed of cart 2 is 0. It's not moving. The final speed is this right here, where it's going from here to, let's say here. So it's going up 1, 2, 3, or excuse me, 0.1, 0.2, 0.3 over 1 second. So 0.3 meters per second. Again, how did you find these speeds from the graph? Slopes. Does this evidence indicate that momentum is conserved during the collision? Well, to figure that out, you have to find the total momentum before and after collision. So let's figure this out. Before collision, the momentum of object 1 before collision is mass times velocity, m1 v1 initial, and that's going to be the 0.3 kilograms, that's mass 1, times the 0.4 meters per second that it's moving, which is 0.12 kilograms meters per second. Keep in mind, P2 initial is 0 because cart 2 is not moving. Well, after collision, P1 final is M1 V1 final, and that one's going to be 0.3 kilograms times the negative 0.1 meters per second. So that would be negative 0.03 kilograms meters per second. And P2 final would be M2 V2 final, or 0.5 kilograms times 0.3 meters per second, or 0.15 kilograms meters per second. And of course, if you add those two together, what do you get? P final equals 0.12 kilograms meters per second. Since total momentum is conserved before the collision equals the total momentum after collision, the total momentum has been conserved, because total momentum before collision equals total momentum after collision. As a result of the collision, what is the impulse applied to cart 1? Okay, so the impulse applied is the change in momentum, and that's the momentum of cart 1 after minus the momentum of cart 1 before. So this would be, if we look at our momenta calculations above, after would be negative 0.03 kilograms meters per second, minus before, that would be 0.12 kilograms meters per second, and we get negative 0.15 kilograms meters per second. Part 2, the impulse or the change in momentum is going to be P2 final, so P2 prime minus P2. So this one is going to be 0.15 kilograms meters per second. That would be this. Minus 0. That would be this. Which is, of course, 0.15. You can see that the impulses are equal and opposite to each other. During the collision, what is the average force applied to? And you can see the time interval is the delta t is 1 second. Remember, the collision occurs between 2 and 3 seconds. So it's 1 second for the collision. And so if J is the impulse, and that's delta t, and that's F delta t is the same as change in momentum, then means force is equal to the change in momentum over delta t. So for Part 1, it's negative 0.15 Newton seconds. I'm going to use Newton seconds instead of kilograms meters per second. It's in the same unit. Divided by 1 second, you can see that we're talking 0.15 newtons of force. For Part 2, same thing. Momentum over the time, we're looking at 0.15 Newton seconds over 1 second. And we're looking at 0.15 newtons. Not only are we seeing equal and opposite impulses, well, that kind of goes along with Newton's third law, equal and opposite forces. Okay, well, what type of collision is this? Well, let's find out the kinetic energy beforehand, afterwards, and we'll be able to tell. So before we're moving, we only have mass 1, which is 0.3, times its velocity of 0.4 meters per second. Multiply 0.4 squared times 0.3, take half, and we get 0.024 joules. The kinetic energy afterwards is going to be 1/2 times mass 1, and its velocity afterwards is 0.1 squared, plus the other mass, 0.5, times its velocity of 0.3 squared. Well, the first mass has a kinetic energy of 0.0015 joules, and the second one has a kinetic energy of 0.0225 joules, for a total kinetic energy of 0.024 joules. So you can see the kinetic energies are the same. Since total kinetic energy is conserved before and after collision, this is an elastic collision. Now let's go to section 5.5, skills for analyzing problems using the impulse momentum equation. Stopping car example. Now this is very similar to one we did in the workbook together in class. A toy car has a mass of 3 kilograms, initially moves at 4 meters per second. Well, we can draw that. I'm going to use black to represent the car, and then blue to represent the impulse of the car. So here we go. Let me draw we had 3 kilograms and 4 meters per second. So I'm going to go up 4 and over 3, just like that. And there's my initial momentum of the car, which would be 12 units. So the initial momentum of the car, which I'm going to call P1 initial, is equal to 3 kilograms times 4 meters per second, which is 12 kilograms meters per second. Now, the car is coming to a stop, and the gentle stop is going to be applied over a longer time interval. The emergency stop is going to be applied over a shorter time interval. So here's the deal. In order for the car's final momentum to be 0, that means you have to apply a negative impulse. Here, the impulse would have to be, in this case, negative 12 kilograms meters per second to zero out or cancel the 12 that you have there. Well, how do we do that? Because now we have a forced time graph. Well, let's just say we're going to apply this over, since we weren't given an actual time in the problem, I'm just going to assume a longer time, like 6 seconds. So if we're looking at not 3 kilograms, so 6 seconds, 6 seconds would be like this, like that, but then you'd have to box in 2 rows deep because the total has to be negative 12, right? And if we make a longer time, such as 6 seconds here, the force would be 2 newtons, or negative 2 newtons here. But that negative 12 is going to balance that positive 12 to give you 0 momentum. Now, the emergency stop is quite similar. You start off with the same initial values right here, but this time it's going to be taking place, and you still need an impulse of negative 12 to bring the final momentum down to 0. So not much is changing, but what is going to change is an emergency stop is taking place under a shorter time. So shorter time interval, gentle stop, longer time interval. So I might give my 12 momentum units looking like this maybe, where it's taken place in a third of the time, like say 2 seconds as opposed to 6 seconds. Six seconds, it was 2 newtons of force. 2 seconds, this is a much shorter time. And you can see that's what, 6 newtons of force? Negative 6 newtons of force, because it's slowing the car down. Again, we end up with 0 momentum units. Okay, so let's apply this to an egg and sheet demonstration.
Hutch, I'm Hutch. This is the science. If you throw an egg into a wall made of bed sheet, it will not break. Go!
Okay, so as we saw in that video, when you throw an egg against a wall, obviously it's going to break. But as you saw, every time it was thrown as hard as you can against a bed sheet, it never broke. So when a teacher or anybody throws an egg against the bed sheet, the egg hits the bed sheet and then rolls gently down towards the floor. The final momentum of the egg is still brought to 0, like when the egg hits the wall. Since the egg collides with the bed sheet with much greater time interval than it did when colliding with the wall, the egg experiences significantly less force and thus does not crack. Okay, we're going to take a look at our final 2 examples here. Bounce or no bounce? A toy car has a mass of 4 kilograms and moves initially forward with a speed of 3 meters per second. Okay, so let's draw the momentum of the car. So 3 meters per second, 4 kilograms. Well, that would look like that. Okay. Consider the following two cases. The car crashes into a wall and stops all of a sudden. The car crashes into a wall and bounces backwards with a speed of 3 meters per second after the collision. Okay, in both cases, the car is only in contact with the wall for 2 seconds. That's going to be helpful for the impulse to know how wide to make the bar graph, 2 seconds wide. Diagram the following situations. Okay, so here we go. In case one, we stop. The final momentum is brought to 0. So what does that mean? I've got, I drew 12. I drew 15, didn't I? Sorry. Let me fix that. 4 times 3 would be 12 momentum units. So it would be this bar graph right here. There we go. There we go. So in the case 1 would be 12 kilograms meters per second. The impulse that would need to be applied here, the change in momentum, would have to be negative 12. And I'll use Newton seconds. Remember, Newton seconds and kilograms meters per second are the same unit. But it's got to be negative to drop 12 down to 0. So how do I draw that? Well, if it's done for 2 seconds, that means it's going to be 6 newtons of force. So 6 newtons of force was required to do that. Now, in the second example, crash and bounce, we start the same initial quantity that we did before, like that. But this time, the car is going 3 meters per second. The car was, keep in mind, it was 4 kilograms. So now it's going 3 meters per second backwards. So how's that possible? Well, to go 3 meters per second backwards, now you're looking at the car having a negative momentum. So in other words, I would draw it just like this. That's the same 4 kilogram mass. And the negative 3 meters per second. So the final momentum is negative 12 kilograms meters per second. Now, how do I go from 12 to negative 12? The only way I do that is if I have a change in momentum, of negative 24 Newton seconds. Well, remember, it's applied over 2 seconds, so you can see it's going to extend way off my page here. It'll be 2 seconds and then down to what? Negative 12, right? So it'll be 12 newtons of force. So it's double the force in order to make that happen. But you'd have to make it longer than the graph is. Okay, and so in the 1950s, cars were made out of solid steel so that they bounced off each other when they were collided. Cars back in those days, there was a thing called the demolition derby, in which cars were simply smashed into each other for recreation, for fun, right, for entertainment. Still happens today, but it's only done with older cars. You never really see demolition derbies with newer vehicles. Otherwise, they would just get crunched in total on the first hit. Well, anyway, these cars today are built of fiberglass materials, plastic, even some aluminum. Although the chassis that holds the occupant compartment, is made of steel, the surrounding areas of the hood where the engine is and the trunk and the side panels, those are all made of very flimsy material. Well, the speed limits during the times are about the same, and the people in both time periods have about the same mass, more or less. During which time period were injuries worse? Answer in a complete sentence. Well, injuries were worse in the 1950s. Here is why. This is because cars were made out of solid steel and had no give during a collision. This means that the momentum would have been brought to 0 under a very short time interval. A very large force would then be applied to the occupants of the car. Cars today have a crumple zone in the front and rear sections of the car to allow give during the collision. The give allows there more time and thus an increase in the force, the time is increased and the force on the occupants of the car will be lessened.